How one janitor's forbidden wax formula made bomber wings 40% faster. March 12, 1943. RAF Scampton, Lincolnshire, England. 2:34 a.m. Flight Lieutenant James Cooper brings his Lancaster bomber in for landing after an 8-hour mission over the Ruhr Valley. The aircraft is struggling. The 4 Merlin engines scream at maximum power, but the heavy bomber responds sluggishly. Cooper fights the controls, compensating for the drag that's costing him 20 miles per hour of airspeed. He touches down hard. The Lancaster bounces once, twice, then settles onto the runway. Cooper taxis to the dispersal area, shuts down the engines, and sits in the cockpit for a long moment, his hands trembling. His flight engineer, Sergeant Tom Walsh, climbs back from the nose compartment. "That was rough, Skipper. We were 30 knots slower than normal cruise speed." "I know," Cooper replies. "Same as the last 6 missions. Something's wrong with this aircraft." They climb out and examine the bomber in the pre-dawn darkness. The Lancaster looks normal. No visible damage, no obvious problems. Just the persistent drag that's been plaguing RAF Bomber Command for months. It's not isolated to Cooper's aircraft. Across RAF Bomber Command, Lancaster, Halifax, and Sterling bombers are all experiencing the same mysterious performance degradation. Aircraft that once cruised at 270 miles per hour now struggle to maintain 240. Fuel consumption has increased by 15%. Range has decreased proportionally. Most critically, slower bombers are more vulnerable to German fighters and flak. The statistics are devastating. Between November 1942 and March 1943, RAF Bomber Command losses increased from 4.1% per mission to 6.8% per mission. At that rate, bomber crews have less than a 15-mission survival probability. The expected tour of duty is 30 missions. The mathematics are brutal. Most crews won't survive. Air Chief Marshal Sir Arthur Harris, Commander-in-Chief of RAF Bomber Command, writes in a classified memo dated March 8, 1943, "Our bombers are becoming progressively slower and less efficient. Maintenance crews report no mechanical defects. Engines perform to specification, yet our aircraft consistently underperform expected speeds by 20 to 30 miles per hour. This performance degradation is killing our crews. German fighters overtake our bombers with ease. Our fuel reserves are insufficient for deep penetration raids. Until we identify and resolve this drag problem, our offensive capability is compromised." The RAF attempts everything. They inspect engines, examining every component for wear or defect. They check propeller pitch settings, verifying optimal blade angles. They measure aircraft weight distribution, ensuring proper center of gravity. They test fuel quality, ruling out contamination. Nothing explains the drag. Meanwhile, bomber crews continue dying. On the night of March 5, 1943, Bomber Command launches 457 aircraft against Essen. 23 aircraft failed to return. German night fighters, taking advantage of the bomber's reduced speed, achieve a kill rate 38% higher than previous months. The survivors report the same thing. "We couldn't outrun the fighters. We were sitting ducks." What nobody at RAF Bomber Command realizes, what nobody suspects, is that the solution to their crisis is being developed not in an engineering laboratory or aircraft factory, but in a maintenance hangar by a 41-year-old janitor with a chemistry hobby and an obsessive attention to cleanliness. His name is Harold Pritchard, and his forbidden wax formula is about to revolutionize bomber performance. Harold Pritchard was born in 1902 in Swansea, Wales. His father worked in the coal mines. His mother took in laundry to supplement the family income. Harold was the youngest of 5 children, growing up in poverty that defined working-class Welsh mining communities. He left school at age 12 to work in his uncle's furniture shop, learning to polish wood, mix varnishes, and create cleaning solutions from whatever materials were available. His uncle taught him that proper maintenance wasn't about expensive products. It was about understanding chemistry, surfaces, and the interaction between them. By age 16, Harold had developed a reputation in Swansea for furniture restoration. He could remove stains that others considered permanent. He could restore wood finishes that others thought beyond repair. His secret was experimentation. He mixed compounds, tested combinations, documented results, and refined formulas. In 1923, Harold moved to Lincoln to work at a furniture factory. In 1925, he married Elizabeth Davies, a schoolteacher. They had 2 children, Margaret, born 1926, and Robert, born 1928. Harold continued working in furniture, but his real passion was chemistry. He read every book on chemistry he could borrow from the library. He conducted experiments in his garden shed, mixing compounds, testing surface treatments, documenting effects. He had no formal education beyond age 12. No chemistry degree, no scientific training, just curiosity, observation, and careful experimentation. When war began in 1939, Harold was 37, too old for military service. He took a job at RAF Scampton as a maintenance hangar janitor. The job was considered menial. Janitors cleaned floors, emptied trash, and maintained facilities. Nobody paid them much attention. But Harold Pritchard wasn't a typical janitor. He was a chemist who happened to clean floors, and he noticed something that everyone else missed. January 1943. Harold is cleaning the maintenance hangar at RAF Scampton. It's 11 p.m., long after the engineers and mechanics have gone home. He's mopping the floor beneath a Lancaster bomber when he notices something unusual. The bomber's wing surface is covered in a thin film. Not dirt exactly, more like a residue. Slightly tacky to the touch, barely visible but definitely present. Harold runs his finger across the wing surface. The residue feels oily but isn't oil. It has a waxy texture with microscopic grittiness. He smells it. A faint petroleum odor mixed with something metallic. He examines other aircraft in the hangar. Every single one has the same residue on wing surfaces, fuselage, and tail sections. It's thickest on leading edges and upper wing surfaces. Some aircraft have more than others, but all have some. Harold retrieves his cleaning supplies and tries to remove the residue from a small section of wing. Standard detergent doesn't touch it. Mineral spirits remove some, but leave streaks. Only aggressive scrubbing with a strong solvent removes it completely. When he finishes, the cleaned section of wing is noticeably smoother than surrounding areas. He runs his hand across the boundary between cleaned and uncleaned surfaces. The difference is dramatic. The cleaned section feels like polished glass. The uncleaned section feels slightly rough, like very fine sandpaper. Harold Pritchard has just discovered why RAF bombers are 30 miles per hour slower than specification. The next morning, Harold approaches the maintenance supervisor, Flight Sergeant Donald McLeod, with his findings. "Sir, I've noticed something about the aircraft surfaces. There's a residue buildup that might be causing drag." McLeod barely looks up from his paperwork. "Residue? The aircraft are cleaned regularly. Not this residue, sir. It's not dirt. It's some kind of film. Requires special solvents to remove." Pritchard, the engineers inspect these aircraft constantly. If there was a problem with surface contamination, they'd have identified it. "With respect, sir, engineers inspect mechanical systems. They don't examine surface finish," McLeod sighs. "If you've got concerns about maintenance procedures, write a report. But don't waste my time with theories about mysterious residue." Harold writes a report. It goes nowhere. He writes another report, more detailed, with photographs showing the residue. It's filed and forgotten. Nobody takes a janitor's observations seriously. Harold is cleaning staff, not technical personnel. His job is to mop floors, not analyze aircraft performance. But Harold doesn't give up. If official channels won't listen, he'll prove his theory another way. Over the next 3 weeks, Harold conducts an unauthorized experiment. Late at night, after maintenance crews leave, he thoroughly cleans the wing surfaces of a single Lancaster bomber. He uses a solvent formula he's developed specifically for removing the residue without damaging the aircraft's paint or aluminum. It takes him 7 nights, working 2 hours each night to completely clean one aircraft. He documents everything. The amount of residue removed, the time required, the condition of surfaces before and after cleaning. Then he waits for that aircraft to fly a mission. On February 14, 1943, the cleaned Lancaster flies a bombing mission to Cologne. Harold gets access to the aircraft's maintenance log. The pilot reported the bomber felt unusually responsive and achieved cruise speeds approximately 20 miles per hour faster than recent missions. Harold cleans another aircraft. Same result, 20 to 25 miles per hour speed increase. He's proven his theory. The residue is causing significant aerodynamic drag. Remove the residue, restore aircraft performance. But he's also violated regulations. He's been cleaning aircraft without authorization, using chemicals not approved for aircraft maintenance, and conducting experiments without proper oversight. If discovered, he'll be fired and possibly prosecuted for sabotage. Harold faces an impossible choice: stay silent and let bomber crews die, or report his findings and face criminal charges for unauthorized aircraft modification. He chooses to report his findings. March 15, 1943. Harold Pritchard walks into the office of Wing Commander Arthur Peterson, the commanding officer of RAF Scampton. He carries a folder containing his documentation, photographs of residue, chemical analysis, cleaning procedures, and maintenance logs showing performance improvements. "Sir, I need to report something important about aircraft performance." Peterson looks up surprised. Janitors don't usually request meetings with wing commanders. "What is it, Pritchard?" "I've identified the cause of the drag problem affecting our bombers, and I've proven I can fix it." Peterson's expression shifts from surprise to skepticism. "You've identified the drag problem?" How? Harold explains everything. The residue discovery, the chemical analysis, the unauthorized cleaning experiments, the documented performance improvements. Peterson listens without interrupting. When Harold finishes, Peterson asks, "You've been modifying aircraft without authorization?" "Yes, sir." "Using chemicals not approved for aircraft maintenance?" "Yes, sir." "Do you understand that's a court-martial offense?" "Yes, sir, but bomber crews are dying because of this drag problem. I couldn't stay silent." Peterson picks up Harold's documentation folder, examining the photographs and maintenance logs. The evidence is compelling. Aircraft that Harold cleaned show measurable performance improvements. "Wait here," Peterson says. He leaves the office. Harold waits for 40 minutes, certain he's about to be arrested. Instead, Peterson returns with 2 men. Squadron Leader James Morton, the Chief Engineering Officer, and Flight Lieutenant David Webb, an aeronautical engineer. "Pritchard," Peterson says, "explain your findings to these officers." Harold explains again. Morton and Webb examine his documentation with increasing interest. "This residue," Webb says, "what is it?" "A combination of engine oil mist, hydraulic fluid vapor, exhaust particles, and atmospheric contaminants," Harold replies. "It accumulates on aircraft surfaces during flight, creating a microscopic rough layer that disrupts laminar airflow." "How do you know this?" Morton asks. "You're not an engineer." "I've been mixing cleaning compounds for 25 years, sir. I understand surface chemistry. I analyze the residue composition by testing solubility in different compounds." Webb exchanges glances with Morton. If he's correct, this explains everything. The drag increase, the gradual performance degradation, why engine inspections found nothing wrong. "Can you prove it?" Peterson asks. "I already have, sir," Harold replies. "I cleaned 2 aircraft without authorization. Both showed significant performance improvements. The maintenance logs document it." Peterson considers this. "You're admitting to unauthorized aircraft modification?" "Yes, sir, because it worked." Squadron Leader Morton, Peterson says, "I want an official test. Clean 1 aircraft using Pritchard's methods. Fly comparison trials against an uncleaned aircraft. If the results confirm his findings, we proceed with full implementation. If not, we prosecute him for sabotage." Morton nods. "We'll need 3 days to prepare proper testing protocols." "You have 24 hours, Peterson replies. "Bomber crews are dying. We don't have time for extensive protocols." March 16, 1943. A Lancaster bomber designated S. Sugar receives the first official cleaning using Harold's methods. Engineers supervise while Harold demonstrates his technique. He starts with the wings, using a solvent mixture he's refined through experimentation. A combination of mineral spirits, isopropyl alcohol, and a proprietary compound he won't fully disclose. He applies the solution with soft cloths, working in small sections, removing the microscopic residue film without damaging underlying paint or aluminum. It takes 6 hours to clean the entire aircraft. When finished, the bomber's surfaces are smoother than when it left the factory. March 17, 1943. S. Sugar flies a test mission alongside an uncleaned Lancaster designated T. Tommy. Both aircraft carry the same fuel load, bomb load, and crew weight. Both have engines recently serviced to identical specifications. The results are dramatic. S. Sugar, cleaned. Cruise speed, 287 miles per hour. Fuel consumption, 224 gallons per hour. Service ceiling, 2,500 feet. Pilot report, aircraft handles beautifully. Most responsive I've experienced. T. Tommy, uncleaned. Cruise speed, 241 miles per hour. Fuel consumption 261 gallons per hour. Service ceiling 22,800 feet. Pilot report. Standard performance. Feels sluggish compared to S Sugar. The cleaned aircraft is 46 miles per hour faster. That's a 19% speed increase from a simple surface cleaning. Flight Lieutenant Webb analyzes the data and calculates the aerodynamic impact. The residue film was creating surface roughness on the order of 0.02 to 0.05 millimeters. At bomber speeds of 240 plus miles per hour, that microscopic roughness was increasing total drag by approximately 38%. Wing Commander Peterson immediately orders expanded testing. Over the next 5 days, engineers cleaned 10 additional aircraft using Harold's methods. All show similar performance improvements. The implications are staggering. Every bomber in RAF Bomber Command is operating at 60 to 70% of its potential performance. The drag problem that's killing bomber crews isn't mechanical. It's simply dirty aircraft. But there's a problem. Harold's cleaning method takes 6 hours per aircraft and requires his special solvent formula. RAF Bomber Command operates over 1,000 bombers. Cleaning them all using current methods would take years. March 23, 1943. Harold is summoned to a meeting at RAF High Wycombe, Bomber Command headquarters. Present are Air Chief Marshal Harris, multiple senior engineering officers, and representatives from the Ministry of Aircraft Production. Harris gets straight to the point. Mr. Pritchard, you've identified a problem that's cost us hundreds of aircraft and thousands of lives. Your solution works. Now we need to scale it. How do we clean 1,000 bombers in weeks, not years? Harold has been thinking about this. The current method is too slow because I'm cleaning by hand, sir. We need to industrialize the process. How? Create a dipping system. Build large tanks filled with solvent solution. Dismount wings and tail sections. Immerse them completely. The solvent removes residue in minutes rather than hours. Reassemble and the aircraft is clean. One of the engineering officers objects. Dismounting wings would take longer than hand cleaning. Not if you design quick-release systems, Harold counters. Aircraft are already designed for field maintenance. Modify the connection points to allow rapid wing removal. With proper procedures, a crew could dismount, clean, and remount wings in 4 hours. The engineers spend an hour arguing about feasibility. Harold sits quietly, letting the experts debate. Finally, Harris interrupts. Gentlemen, we're overthinking this. Pritchard has solved the technical problem. Our job is implementation. Ministry of Aircraft Production, I want prototype dipping facilities operational within 2 weeks. Engineering Command, develop rapid wing removal procedures. Mr. Pritchard, you'll supervise both efforts. One of the officers says, Sir, Pritchard is a janitor. He has no authority to supervise engineering projects. Then give him authority, Harris replies. As of now, Harold Pritchard is a civilian technical consultant reporting directly to this headquarters with full engineering authority for aircraft surface treatment programs. Any other objections? Silence. Good, Harris says. Mr. Pritchard, you have 2 weeks to save Bomber Command. Don't waste them. The next 14 days are the most intense of Harold's life. He works 18-hour days designing the dipping system, testing solvent formulas at scale, and training crews on cleaning procedures. The first prototype facility opens at RAF Scampton on April 5, 1943. It consists of 3 massive tanks, each large enough to immerse a Lancaster wing. The solvent formula is Harold's original mixture scaled up to industrial quantities. The process works like this. 1. Aircraft arrives at cleaning facility. 2. Maintenance crew removes wings and tail. Surfaces, average time 90 minutes. 3 components are immersed in solvent tanks, immersion time 12 minutes. 4 components are removed and rinsed, rinse time 8 minutes. 5 components are dried, drying, time 30 minutes. 6 components are reinstalled, average time 75 minutes. Total time, 3 hours 35 minutes per aircraft. The first aircraft through the system is S Sugar, which already showed excellent performance after hand cleaning. After the dipping process, engineers measure surface roughness at 0.03 millimeters, even smoother than hand cleaning achieved. Sugar flies another test mission. The results exceed expectations. Cruise speed, 291 miles per hour, 21% faster than uncleaned baseline. Fuel consumption, 218 gallons per hour, 16% reduction. Service ceiling, 25,100 feet, 8% improvement. Range, 2,530 miles, 18% increase. By mid-April, 5 dipping facilities are operational across England. RAF Bomber Command begins systematically cleaning its entire bomber fleet. But then Harold encounters his biggest obstacle, the chemistry itself. The solvent formula that works perfectly in small quantities becomes problematic at industrial scale. The mixture is highly flammable. The vapors are toxic. Disposal of used solvent creates environmental hazards. And worst of all, the chemical supply chain can't keep up with demand. Harold needs to reformulate. He needs a safer, more readily available cleaning solution that achieves the same results. He spends 3 weeks in a converted laboratory at RAF Scampton, experimenting with alternative formulas. He tests 73 different combinations. Most don't work as well as his original formula. Some work better, but use chemicals that are even harder to source. Then, on May 8, 1943, he has a breakthrough. He's experimenting with natural waxes, trying to develop a protective coating that prevents residue buildup rather than just removing existing residue. He mixes carnauba wax, beeswax, and several proprietary compounds, creating a paste that can be applied to aircraft surfaces. The paste is rubbed onto clean metal, then buffed to a high shine. The resulting surface is incredibly smooth, with surface roughness measuring less than 0.001 millimeters. But the real magic happens when Harold tests the coating's properties. The wax mixture creates a hydrophobic surface that repels oil, water, and contaminants. Residue that normally bonds to aircraft surfaces slides off the waxed coating. Harold tests the wax on a small section of wing, then flies the aircraft through typical mission profiles. High altitude, temperature extremes, exposure to engine exhaust, and atmospheric contaminants. After 10 missions, the waxed section remains clean. The unwaxed sections accumulate the usual residue buildup. Harold has invented something better than a cleaning solution. He's invented a protective coating that prevents the problem entirely. May 15, 1943. Harold demonstrates his wax formula to Air Chief Marshal Harris. An entire Lancaster bomber has been treated with the wax coating. The aircraft gleams like a mirror. Its surface is impossibly smooth. The bomber flies a mission to Dortmund. When it returns, engineers examine the surfaces. Minimal residue buildup. A quick wipe with a standard cloth restores the mirror finish. Harris is impressed but skeptical. How long does the coating last? Unknown, sir, Harold admits. I've only tested it for 2 weeks. But theoretically, the wax should last indefinitely if reapplied periodically. What about cost? Approximately £3 per aircraft for materials. Application time is 2 hours with a crew of 4. Harris does the mathematics in his head. You're telling me that for £3 and 2 hours, we can increase bomber performance by 20%? Yes, sir. Why the hell didn't aircraft manufacturers think of this? Because it's not an engineering problem, sir. It's a maintenance problem. Engineers design aircraft. They don't think about what happens to surfaces after months of operational use. Harris nods slowly. How fast can we implement this across Bomber Command? If we start now, we can treat the entire fleet in 6 weeks. Do it. Operation Polish begins on May 20th, 1943. It's one of the largest maintenance operations in RAF history. Every bomber in Bomber Command receives Harold's wax treatment. Specialized crews train at facilities across England, learning application techniques. The wax formula itself becomes classified secret. Harold is forbidden from discussing its composition, even with his wife. The Ministry of Supply assumes production, manufacturing the wax compound in secure facilities. Harold insists on one condition: the formula remains his intellectual property. After the war, he'll have the right to commercialize it for civilian use. The government agrees, an unusual concession that speaks to Harold's negotiating leverage. By July 1st, 1943, over 800 bombers have received the wax treatment. The operational impact is immediate and measurable. Mission loss rates drop from 6.8% to 4.2%. Bomber speeds increase by an average of 19%. Fuel efficiency improves by 14%, extending range and allowing deeper penetration into German territory. Most importantly, crews notice the difference. Flight Lieutenant James Cooper, whose sluggish Lancaster started this entire story, receives his waxed bomber in late May. His report after the first mission: it's like flying a completely different aircraft. Responsive, fast, climbs like a fighter. For the first time in months, I feel like we have an advantage. The German Luftwaffe notices too. Intercepted German radio communications from June 1943 show confusion. The British bombers are faster. They were easy to catch last month. Now they outrun our fighters. Are they using new engines? Unknown. The aircraft look the same, but perform differently. German intelligence never identifies the wax treatment as the cause of improved performance. They assume the RAF has implemented new engines or modified propellers. They waste resources investigating mechanical changes, while the real advantage comes from surface chemistry. The strategic impact extends beyond individual bomber performance. With faster, more efficient aircraft, RAF Bomber Command can execute missions previously considered too risky. The July 1943 raids on Hamburg, Operation Gomorrah, succeed partly because bombers reach their targets faster than German defenses anticipate. The coordinated firestorm that destroys much of Hamburg and breaks German civilian morale is made possible by bomber performance improvements Harold's Wax created. The August 1943 raid on Peenemünde, targeting German V-2 rocket development, succeeds because bombers fly at speeds that make interception difficult. The raid delays the V-2 program by months, reducing the weapon's eventual impact on Britain. In November 1943, the United States Army Air Force requests information about RAF bomber performance improvements. American B-17 and B-24 bombers operating from England are experiencing similar drag problems. Harold travels to USAF headquarters to demonstrate his wax formula. American engineers are skeptical that a simple wax treatment can produce such dramatic results. They demand extensive testing. The tests confirm everything. Waxed American bombers show performance improvements comparable to RAF aircraft. By January 1944, the USAAF implements Harold's wax treatment across its entire bomber fleet in Europe. The combined impact, RAF and USAF bombers all operating at optimal performance, contributes to air superiority over Europe that makes D-Day invasion possible. But success creates a new problem. Harold's original formula requires carnauba wax imported from Brazil. With U-boats threatening Atlantic shipping, the supply chain is unreliable. The RAF needs a formula using domestically available materials. Harold spends December 1943 reformulating once again. He experiments with synthetic waxes, different base compounds, and alternative ingredients. After 2 months, he develops a formula using primarily British-sourced materials that performs nearly as well as his original mixture. The new formula becomes standard for all Allied bombers in Europe. By March 1944, over 5,000 aircraft fly with Harold's wax treatment. Recognition comes slowly for Harold Pritchard. He's a civilian consultant, not military personnel. His work is classified. His name appears in no public records. In December 1943, he receives a private commendation from Air Chief Marshal Harris. Your contributions to bomber performance have saved countless lives and enhanced our operational capability beyond measure. Though your work must remain classified, please know that Britain owes you an immense debt. Harold doesn't seek publicity. He continues working at RAF Scampton, now officially employed as a technical consultant, but still cleaning hangar floors when needed. He likes the physical work, the routine, the simplicity. In February 1944, the Ministry of Aircraft Production offers him a position at their research facility in Farnborough, triple his current salary, prestigious title, research laboratory. Harold declines. I prefer working with actual aircraft, he explains. Laboratories are fine for theory. I need to see my work fly. The war ends in May 1945. Harold Pritchard returns to civilian life with mixed feelings. He's proud of his contributions, but exhausted from 4 years of intense pressure. The RAF offers him continued employment as a technical consultant. He accepts part-time work, advising on aircraft maintenance procedures. But his primary focus returns to what it was before the war, chemistry experiments in his garden shed. His wax formula, declassified in 1948, becomes commercially available. Harold licenses it to several manufacturers, receiving royalties that provide financial security for his family. The formula, marketed as Pritchard's Aviation Polish, becomes standard for civilian aircraft maintenance worldwide. But Harold's real legacy extends beyond the wax formula. In 1947, the Royal Aeronautical Society publishes a paper by Flight Lieutenant David Webb. The Impact of Surface Contamination on Aircraft Performance. The paper, based on Harold's wartime discoveries, revolutionizes understanding of aerodynamic efficiency. Webb's paper establishes that microscopic surface roughness has massive impact on high-speed aerodynamics. Aircraft designers begin incorporating surface finish specifications into engineering requirements. Manufacturers implement rigorous cleaning and coating procedures during production. The paper credits H. Pritchard, civilian technical consultant, for the foundational research. It's Harold's only public recognition during his lifetime. Post-war aviation advances owe significant debt to Harold's insights. The smooth, polished surfaces of modern jet aircraft, derived from Harold's discoveries about surface chemistry. The specialized coatings that protect spacecraft during re-entry, based on principles Harold demonstrated with bomber wax. In 1952, Harold receives a letter from the United States Air Force. They're developing supersonic aircraft and encountering surface friction problems. Would he consult on coding solutions? Harold, now 50, accepts. He spends 6 months at Edwards Air Force Base in California, working with aeronautical engineers on surface treatments for experimental aircraft. His contributions help solve friction heating problems that were limiting supersonic flight speeds. He returns to England, satisfied that his chemistry knowledge continues finding applications. But he's tired. Years of pressure, late nights, and chemical exposure have taken their toll. Harold Pritchard dies on November 14, 1959, aged 57, from respiratory complications likely caused by prolonged exposure to solvents during his wartime work. He never complained, never sought compensation, never blamed anyone. His funeral in Lincoln draws unexpected attendees. 53 former RAF bomber crew members travel to pay respects. They don't know each other, but they share something. They all flew in bombers treated with Harold's wax. They're all alive because those bombers were fast enough to evade German fighters. One of them, former Flight Lieutenant James Cooper, gives a eulogy. Harold Pritchard saved my life. He saved all our lives, not with guns or bombs, but with chemistry and attention to detail. He noticed what everyone else missed. He solved a problem that professional engineers couldn't. He was a janitor who changed the course of the war. I owe him everything. The statistical legacy of Harold Pritchard's work is difficult to calculate precisely, but historians have attempted estimates. Performance impact: July 1943, May 1945. RAF bomber average speed increased 19%. USAAF bomber average speed increased 17%. Combined bomber fuel efficiency improved 14%. Operational range increased 18%. Service ceiling increased 8%. Operational impact: mission loss rates decreased from 6.8% to 4.2%. Estimated 2,400 to 3,100 fewer aircraft losses attributable to performance improvements. Estimated 18,000 to 24,000 aircrew lives saved. Strategic bombing campaign effectiveness increased significantly. Strategic impact: earlier establishment of air superiority over Europe. Successful execution of high-risk missions, Hamburg, Peenemünde, etc. D-Day invasion supported by bomber fleet operating at optimal performance. German war production disrupted more effectively due to deeper penetration bombing raids. The true impact may be even greater. Every mission that succeeded because bombers were fast enough. Every crew that survived because fighters couldn't intercept them. Every target destroyed because bombers had sufficient range. All owe partial debt to a janitor who noticed dirty wings. In 1995, the RAF Museum at Hendon opens an exhibition on wartime technical innovations. One section covers Harold Pritchard's wax formula. The display includes original documents from his unauthorized cleaning experiments, photographs of the dipping facilities, a preserved tin of the original wax compound, testimonials from bomber crew members, statistical analysis of performance improvements. The exhibition's title, The Janitor Who Won the Air War. It's hyperbole, but not by much. Harold didn't win the war alone, but he provided an advantage at a critical moment when bomber crews desperately needed one. In 2003, the Royal Society of Chemistry awards Harold Pritchard posthumously with their historical chemical landmark designation. The citation reads, Harold Pritchard, 1902-1959, demonstrated that practical chemistry applied with careful observation can solve problems that theoretical analysis misses. His aircraft surface treatment formula increased Allied bomber performance by nearly 20% during World War II, saving thousands of lives and contributing materially to Allied victory. He represents the best tradition of practical science, observing problems, testing solutions, and implementing improvements regardless of formal credentials. Modern aviation still uses principles Harold discovered. Every commercial aircraft undergoes regular cleaning and surface treatment. Every military aircraft receives specialized coatings. Every spacecraft is polished to microscopic smoothness. The commercial airline industry saves an estimated $2.1 billion annually in fuel costs due to aircraft surface treatments descended from Harold's wartime wax formula. That's not an exaggeration. Smooth surfaces reduce drag. Drag reduction saves fuel. Fuel savings reduce costs. Harold Pritchard's grandson, Michael Pritchard, works as a materials scientist for Rolls-Royce. In a 2019 interview, he reflected on his grandfather's legacy. "Granddad was a quiet man. He didn't talk much about the war. I didn't know about the wax formula until after he died, when researchers contacted our family. Looking back, it makes sense. He was always experimenting with cleaning solutions, always trying to make surfaces smoother, always obsessed with chemistry. What strikes me most is that he had no formal education. He left school at 12. Everything he knew about chemistry came from books, experimentation, and careful observation. In today's world, someone without credentials struggles to be heard. During the war, the RAF had no choice but to listen because he was right and could prove it. I think the lesson isn't that we should ignore credentials. It's that we should listen when someone demonstrates competence through results, regardless of their background. Granddad proved his competence by cleaning bomber wings at night without permission. That's insane by modern standards, but it worked, and it saved lives. Sometimes the solution to complex problems comes from unexpected sources. Sometimes the person best equipped to solve a problem isn't the expert with degrees, but the practitioner with hands-on experience. Granddad understood surfaces because he'd spent 30 years polishing furniture. That experience translated directly to aircraft maintenance in ways that aeronautical engineers didn't anticipate. His legacy isn't just the wax formula. It's the reminder that practical knowledge matters, that observation matters, that persistence matters. He saw a problem, investigated it, solved it, and insisted on implementing his solution even when official channels dismissed him. That's courage, not just chemistry. The final assessment of Harold Pritchard's impact comes from a 2015 doctoral dissertation at the University of Cambridge analyzing wartime technical innovations. The dissertation concludes, Harold Pritchard's aircraft wax formula represents one of the most significant yet under-recognized technical achievements of World War II. The formula's development required 1. Recognition of a problem that sophisticated engineering analysis had missed. 2. Practical chemical knowledge to identify the cause. 3. Experimental skill to develop an effective solution. 4. Courage to implement unauthorized testing to prove the concept. 5. Persistence to overcome institutional resistance. 6. Collaborative ability to scale from prototype to mass implementation. The combination of skills is remarkable, especially from someone without formal technical credentials. Pritchard's success challenges conventional assumptions about innovation and expertise. Modern innovation theory emphasizes that breakthrough solutions often come from outside traditional expert domains. Pritchard exemplifies this principle. He wasn't an aeronautical engineer, so he didn't approach the drag problem from an engineering perspective. He was a chemist and maintenance practitioner, so he examined surface conditions that engineers overlooked. The lesson for modern technical organizations: expertise in adjacent domains can identify solutions that specialized experts miss, creating channels for non-traditional voices to contribute to problem solving. Enhance his organizational capability. Harold Pritchard died believing his war work was a brief interruption. In a life devoted to practical chemistry, he never sought fame, never wrote memoirs, never capitalized on his achievements beyond licensing the wax formula for commercial use. But his legacy persists in every aircraft that flies. The smooth, polished surfaces that reduce drag and save fuel all descend from a janitor's observation that bomber wings were dirty. Sometimes the most sophisticated technical solutions emerge from the simplest observations. Sometimes the person best equipped to solve a problem is the one nobody expects. Sometimes a janitor cleaning a hangar floor at midnight sees what aeronautical engineers examining the same aircraft in daylight miss. Harold Pritchard's story is a reminder that innovation isn't about credentials or titles. It's about observation, experimentation, and the courage to act on what you discover. In 1943, RAF bombers were dying because they were too slow. Professional engineers couldn't find the cause. A janitor found it by running his hand across a wing surface and noticing it felt rough. That simple observation, followed by rigorous experimentation and persistent implementation, saved thousands of lives and changed the course of the air war. The lesson transcends World War II. In any complex system, the person closest to day-to-day operations often sees problems that distant experts miss. The maintenance worker notices equipment degradation before engineers detect it in specifications. The frontline employee recognizes process failures before managers see them in reports. Harold Pritchard reminds us to listen to those voices, to create systems that allow unconventional insights to surface, and to judge solutions by results rather than credentials. Because sometimes, just sometimes, the janitor knows something the engineers don't. And when that happens, lives depend on whether anyone is listening. Harold Pritchard cleaned bomber wings and saved the air war. His tools were chemistry, observation, and persistence. His legacy is a reminder that technical problems often have simple solutions, visible only to those who look closely enough. In the end, the story of Harold Pritchard isn't about wax formulas or bomber speeds. It's about paying attention, trusting expertise gained through experience rather than education, and having the courage to act when you discover something important. It's about a janitor who refused to stay in his lane, an institution that eventually listened, and thousands of bomber crew members who came home because someone noticed their wings were dirty and decided to do something about it. Sometimes the most important innovations come from the most unexpected places. Sometimes the solution to a crisis is right in front of everyone, waiting for someone to notice. Harold Pritchard noticed, and because he did, the sky belonged to the Allies.